Hello, today we're going to be discussing real-world applications of calculus concepts, particularly delving into related ideas of physics. Derivatives and integrals can be applied to position, velocity, and acceleration equations to fill in any missing information. If given a function s of t for a particle's position, applying a derivative once will leave you with an equation for the particle's velocity, s prime of t, and applying another derivative will leave you with its respective acceleration equation, s double prime of t. We can also move from acceleration backwards towards the position equation by applying integrals. Taking the integral of the acceleration once will give the velocity antiderivative of t, and applying another integral to the acceleration function gives the position the integral of the antiderivative of a of t dt. If the integral is not on a definite interval, solving for the value c is necessary, also known as s at time 0 is equal to c.
The position of an object is the object's location relative to a specific starting point. Velocity is the rate of change of position measured in units of distance divided by time. Many times the terms velocity and speed are interchanged in common speech. However, each term has a different meaning in calculus. In a vertical plane, the upward motion of an object typically gives a positive velocity, while downward motion gives a negative velocity. If the desired motion of the object is strictly horizontal, moving forward normally gives a positive velocity, and moving backward gives a negative velocity. These may change depending on what direction is considered positive and what direction is considered negative. Speed, on the other hand, is always positive, so while direction may matter to velocity, it does not impact speed. Acceleration is the rate of change of velocity.
So, acceleration, being the rate of change of position, qualifies it as the second derivative of the initial function s of t, or position. The rate of change of s of t is the first derivative, being v of t, or velocity.
What does it mean if the y value of one of these functions remains constant over a certain interval? If the function in question is position, the object is at rest. If the y value of velocity is constant, then the position is always changing at a steady rate. If the y value of acceleration remains constant, like in this example, velocity is always changing at a steady rate, so the position will be rapidly moving in a positive direction as the velocity increases. Likewise, the position will be rapidly moving in a negative direction if the velocity is constantly decreasing. Let's work through a problem where the y value of the acceleration equation remains constant. Our example position equation is st is equal to 3t squared plus 10t plus 2. The velocity equation is then s prime of t is equal to 6t plus 10, leaving the acceleration equation as s double prime t is equal to 6.
If we are given our first equation of position, we can use derivatives, as previously stated, to solve for other two equations. Let's illustrate this concept using this equation here, 3t squared plus 10t plus 2. Taking the derivative of 3t squared will give us 6t, taking the derivative of 10t will give us just 10, and taking the derivative of 2 will give us a value of 0. So ultimately, our velocity equation is 6t plus 10. To find the acceleration, taking the derivative of our now found velocity equation, or the second derivative of our position equation, will leave us with a constant value of 6, since the derivative of 6t is 6, and the derivative of 10 is 0. Since this is a scientific as well as a mathematical idea, we also have to discuss units. The position equation would have a unit of length like centimeters. Taking the derivative of this to find velocity would mean finding the rate of change of that length respective to the starting position. In reality, this means that you would apply a unit of time, since velocity is a measure of the length traveled per unit of time. This leaves us with the length over time like centimeters per hour. Acceleration is where it gets a little more confusing, since taking the second derivative applies another unit of time to our original position. In essence, this means that we would be finding the rate of change of our velocity, so we'd be finding the velocity per unit of time. Acceleration would look somewhat like the length per time, like centimeters per hour. It is important to note that calculus can be applied to other situations outside of the motion of an object. Examples of this would include the rate at which something is being added to a pile, or the rate at which a three-dimensional figure is shrinking. For conceptualizing this idea, though, we will just be working with the idea of motion.
To head in the reverse direction, or to go from acceleration to velocity to position, we can apply integrals to each of our functions. Taking the integral of the acceleration function at would give the velocity function the antiderivative at, and taking the integral again gives position the integral of the antiderivative at dt. In terms of our example, applying the integral to the acceleration function at equals 6, we get at equal to 6t plus c. This c is known as the constant of integration. What is c, you ask? Well, as we know, the actual velocity function is vt equal to 6t plus 10. However, the starting velocity being 10 is not given because taking the derivative of the 10 left us with 0. This means that that integer would not be counted for when working backwards with integrals. C, in this sense, is a constant that stands in place of this missing integer. Occasionally, a problem will present this information to you that you can then incorporate into your answer. For example, v of 0 is equal to 10, meaning that the starting velocity at time 0 is equal to 10. The same goes for when integrals are applied to velocity to find position.
It is important to note that c can be ignored on definite integrals. We can see this expressed in the example here. If you have the definite integral of 2t plus 3 from 1 to 2, you would have t squared plus 3t plus c evaluated from 1 to 2. Solving this would mean, by the fundamental theorem of calculus, that you would have quantity 2 squared plus 3 times 2 plus c minus the quantity of 1 squared plus 3 times 1 plus c. Our answer would be just 6, as the c's cancel out. This is true for all definite integrals, although c is still necessary for indefinite integrals, as the c would not be expressed in a way that could cancel it out.
Back to our problem, we found the antiderivative at equal to 6t plus c, which we know to be 10 based on the given information. So the antiderivative at equals 6t plus 10. Taking the integral again will leave us with 3t squared plus 10t plus c. This c value is also given as the position at time 0 is equal to 2. So our position equation winds up being 3t squared plus 10t plus 2, which is exactly what we started with.
Okay.